Hi students, welcome to the 10th lecture in permutations and combinations. I hope you have watched all the first 9 lectures. In this lecture we are going to discuss hints and solutions for exercise 5D problems, and I'm going to introduce combinations. Before looking into these things, let me recall what we have done in the first 9 lectures. In the first 9 lectures we have discussed about fundamental principle of counting, both multiplication and addition. So coming to multiplication, if a task T contains two works W1 and W2, then the number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2. And coming to addition, if a task T can be performed in two formats, W1 or W2, then the number of ways of completing the task is equal to number of ways of completing W1 plus number of ways of completing W2. So what you have to remember here is whenever n comes we have multiplication, and whenever r comes we have addition. So these are the two things that you have to remember throughout this chapter. And then we have defined factorials. I think you are familiar with the factorials by this time. And then we have discussed about linear and circular permutations. If you arrange things in a line, then it is going to be a linear permutation. If you arrange things in a circle, then it is going to be a circular permutation. We have discussed about linear permutations and circular permutations in detail. Anyway, the number of linear permutations of n objects taken r at a time is in general denoted by npr, and npr is equal to n times n minus 1 times n minus 2 times so on up to n minus r plus 1. Or else we can give a formula for this one. We can write it as n factorial upon n minus r factorial. I repeat, number of permutations of n distinct objects taken r at a time is in general denoted by npr, and npr is equal to n factorial upon n minus r factorial. So this is the total number of permutations of n distinct objects taken r at a time. And we have few theorems related to this npr. And the first theorem is npr is equal to n times n minus 1 p r minus 1. So we can extend this one and we can still write it as npr is equal to n times n minus 1 times n minus 2 p r minus 2. Anyway, the second result is like this: npr is equal to n minus 1 p r plus r times n minus 1 p r minus 1. So here r times n minus 1 p r minus 1 stands for number of permutations of n distinct objects taken r at a time, which always include a particular object. And n minus 1 p r stands for number of permutations of n distinct objects taken r at a time which do not contain a particular object. And npr stands for number of permutations of n distinct objects taken r at a time. Therefore, number of permutations of n distinct objects taken r at a time is equal to number of permutations without that particular object plus number of permutations with that particular object. And then we have discussed about this one. When repetitions are allowed, then the number of permutations is going to be n raised to r. The number of permutations of n distinct objects taken r at a time when repetitions are allowed is going to be n raised to r. If repetitions are not allowed, then it is going to be npr. If repetitions are allowed, then it is going to be n raised to r. Now, number of permutations in which at least one object is repeated is going to be n raised to r minus npr. So this n raised to r gives the total number of permutations when repetitions are allowed, and npr stands for number of permutations when repetitions are not allowed. Therefore, n raised to r minus npr gives the number of permutations which at least one element, with at least one element repeated. And then we have seen the definition of palindrome. A word or a number when read from right to left or left to right gives the same meaning is called palindrome. And the number of palindromes of length r formed using n objects is given by n raised to r upon 2 when r is an even number, and n raised to r plus 1 upon 2 when r is an odd number. So the length of the palindrome is going to be crucial. If the length of the palindrome is even, then we have to use the first one. If the length of the palindrome is going to be an odd number, then we have to use the second one. And then we have discussed about circular permutations. The number of circular permutations of n distinct objects taken all at a time is going to be n minus 1 factorial. So in this we have a special case called the hanging models. In case of hanging models, the number of permutations is going to be n minus 1 factorial upon 2, because we are considering both clockwise and anti-clockwise permutations as a single permutation. So here, assume that these 3 people are sitting on a table. If I want to swap these two people, then what I have to do is I have to make these 2 people stand, and then I have to change their seats. So coming to this one, so here we have a chain consisting of beats. So here we have 3 different beats. Now if I want to change these 2 beats, the extreme right and the extreme left, then what we have to do is we can just rotate the chain. If you just rotate the chain, then this one occupies this place and this one occupies this place. So we are not removing the beats and we are not rearranging it. Whereas here, if I want to exchange these two, then what I have to do is I have to rearrange. So if I want to exchange these two, then what I have to do is I have to just rotate the chain. That means here we are considering both clockwise and anti-clockwise permutations as a single permutation. So that's why we are dividing it by 2. And then we have permutations with constraints. So in permutations with constraints, if p things are alike in n objects, then the number of permutations is going to be n factorial upon p factorial. And similarly, if we have n objects in which p things are alike and another q things are alike and another r things are alike, then the number of permutations is going to be n factorial upon p factorial times q factorial times r factorial. So these are the things that we have discussed in the first 9 lectures. In the 8th lecture, we have discussed about permutations with constraints. In permutations with constraints, we have these 2 results. So the first result is when p things are alike, then the number of permutations is going to be n factorial upon p factorial. If we have 3 sets of alike things, p, q and r, then the number of permutations is going to be n factorial upon p factorial times q factorial times r factorial. And then we have discussed about example problems. Now let us move on to exercise problems. And the first example exercise problem that I am going to discuss here is find the number of 4-letter words that can be formed using the letters of the word Ramana. R-A-M-A-N-A. I repeat the question. Find the number of 4-letter words that can be formed using the letters of the word Ramana. R-A-M-A-N-A. The solution for this problem is not straightforward. What I mean is we cannot apply the known formulas to solve this problem. If they ask us to find out all 6-digit letters that can be formed using the letters of the word Ramana, then the answer is going to be 6 factorial upon 3 factorial. Because in the letter Ramana there are 3 A's which are identical. And there are 6 letters, therefore the answer is going to be 6 factorial upon 3 factorial. But here they are not asking us to find out all 6-letter words that can be formed using the letters of the word Ramana. Instead, they are asking us to find out all 4-letter words that can be formed using the letters of the word Ramana. You may haven't come across these kind of problems in the earlier exercises. So here we have to select 4 letters. So which 4 letters we have to select, that is the question. So let us try to analyze the question. So we have to find all 4-digit letters that can, 4-letter words that can be formed using the letters of the word Ramana. So first what we have to do is, first we have to find in how many ways we can select 4-letter words or 4 letters from Ramana. So which 4 letters we have to select, that is the question. So I can select 3 letters R, M, N, A. So I can select these 4 letters and then I can form all 4-letter words that can be formed using these 4 letters. or I can write RM double A or RN double A or so MN double A. I can select these 4 letters, or I can select any of these 4 letters, or I can select R triple A or M triple A or N triple A. So first we have to select 4 letters from the given 6 letters. After selecting these 4 letters, then we can find out how many 4 letter words that can be formed using these 4 letters. So try to understand the question first of all. The question is to find how many 4 letter words that can be formed using the letters of the word Ramana. So here what we have to do is first we have to select 4 letters. So after selecting 4 letters, we can write down all the 4 letter words that can be formed using these 4 letters. So I can select 4 letters in any of these choices. I can select 4 letters in this way, or any of these 3 ways, or any of these 3 ways. So on the whole, I can select 4 letters in any of these 7 ways. I repeat, I can select 4 letters in any of these 7 ways. Now we have to count how many 4 letter words that can be formed. So number of 4 letter words that can be formed using the letters R, M, N, A plus number of 4 letter words that can be formed using the letters R, M, double A plus number of 4 letter words that can be formed using R, N, double A plus number of 4 letter words that can be formed using M, N, double A plus number of 4 letter words that can be formed using R, triple A plus number of 4 letter words that can be formed using M, triple A plus number of 4 letter words that can be formed using N, triple A. So this is the precise answer. We have to find how many 4 letter words that can be formed using these combinations. Okay, so first let us find out how many 4 letter words that can be formed using. So 4 letter words that can be formed using the letters R, M, N, A is going to be 4 factorial plus R, M, double A. Number of 4 letter words that can be formed using R, M, double A is going to be 4 factorial upon 2 factorial plus number of 4 letter words that can be formed using R, N, double A. This can be done in 4 factorial upon 2 factorial ways plus number of 4 letter words that can be formed using M, N, double A. This can be done in 4 factorial upon 2 factorial ways plus number of 4 letter words that can be formed using R, triple A. This can be done in 4 factorial upon 3 factorial ways plus number of 4 letter words that can be formed using the letters M, triple A. This can be done in 4 factorial upon 3 factorial ways plus number of 4 letter words that can be formed using the letters N, triple A. This can be done in 4 factorial upon 3 factorial ways. So the total number of 4 letter words that can be formed using is equal to, we have to add all these things. So this is going to be our answer. So this question is a little bit typical question, so you have to be careful while answering this question. So they are not asking us to find out all 6 letter words that can be formed using the letters of the word Ramana. They are asking us to find out all 4 letter words that can be formed using the letters of the word Ramana. If they ask us to find out 6 letter words, then this is the answer. But instead of asking 6 letter words, they are asking us to find out all 4 letter words that can be formed using the letters of the word Ramana. So first what we have to do is, first we have to select 4 letters. So these 4 letters can be selected in any of these 7 ways. So in order to select 4 letters from these R, M, N, A, R, A, M, A, N, A. So we have any of these 7 ways. First I have to select any of these 4 letters in these 7 ways. After that I have to find out how many 4 letter words that can be formed using each combination. So number of 4 letter words that can be formed using R, M, N, A plus number of 4 letter words that can be formed using these 4 letters plus so on, plus number of 4 letter words that can be formed using these R, triple A plus so on. So we have to add all these things. So this is going to be our answer. Our next question is like this. How many numbers can be formed using the digits 1, 2, 3, 4, 3, 2, 1 so that even digits occupy even places? I repeat, how many numbers can be formed using the digits 1, 2, 3, 4, 3, 2, 1 such that even digits occupy, even numbers occupy even digits? So just by looking at this problem, you should realize one more problem. So the relative positions of vowels and consonants are not disturbed. This problem is same as that one. So here let me write down the given numbers. Given numbers are 1, 2, 3, 4, 3, 2, 1. So on the whole we have 7 numbers. So in these 7 numbers we have 2 2s and 1 4 and 2 1s and 2 3s. So the even numbers are 2 2 and 4 and the odd numbers are 1 1 3 3. Now the question is, the even digits occupy even places. So what are the even places here we have? This is my even place and this is my even place. This is my even place and this one. So we have 3 even places and we have 4 odd places. I have to fill these 2 2 4 in these 3 blanks, E E E, and I have to fill 1 1 3 3 in the remaining blanks. So W1 is to fill 2 2 4 in even places and W2 is to fill 1 1 3 3 in odd places. Now number of ways of doing W1 is equal to 3 factorial upon 2 factorial. Since we have 3 numbers, the number of ways of arranging is equal to 3 factorial. Out of these 3 numbers, 2 are identical. Therefore, the answer is 3 factorial upon 2 factorial. The number of ways of doing W1 is 3 factorial upon 2 factorial. And W2, number of ways of doing W2 is equal to 4 factorial upon 2 factorial times 2 factorial. We have 4 numbers, 1 1 3 3. So out of these 4 numbers, we have 2 sets of identical objects. Therefore, number of ways of doing W2 is equal to 4 factorial upon 2 factorial times 2 factorial. Now total number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2. So which is equal to 3 factorial upon 2 factorial times 4 factorial upon 2 factorial times 2 factorial. So if you write these kind of statements, then things will be little bit clear. Okay. The next problem goes like this. A bookshelf has m copies of n different books. Find the number of ways of arranging these books in a shelf in a single row. So we have done similar kind of things. So in the previous examples we have done, in the previous questions we have done, there are 4 different maths books, 3 different chemistry books and 2 different physics books. Find the number of ways of arranging those books in a shelf in a single row. But here what we have is m copies of n different books. So on the whole, the number of books is equal to m times n. But all these m times n books are not different. There are m copies alike of each kind. For example, let us assume that there are 3 copies of 2 different books. That means there are 3 copies of English and 3 copies of Telugu. So instead of having only 2 different books, we have n different books, m copies of n different kinds. The total number of books is going to be mn. Now, number of ways of arranging is equal to so we are going to use this formula n factorial upon p factorial times q factorial times r factorial. So we can use this formula when we have n objects, and out of those n objects there are p objects which are alike, and there are q objects which are alike, and there are r objects which are alike. Here instead of n we have m times n. Instead of n we have m times n. So number of ways of arranging is equal to m times n factorial upon m factorial times so on up to m factorial. So we'll have n times. So on the whole we can just write it as m times n whole factorial upon m factorial raised to n. So we are using this formula n factorial upon p factorial times q factorial times r factorial. So in order to use this formula, we have n objects. Out of these n objects we have p objects of one kind, there are q objects of one kind, and there are r objects of another kind, and the rest of the objects are different. Here there are m times n books. Out of those m times n books, we have m copies of each kind. So there are m books which are alike, and there are another set of m books which are alike, and there are another set of m books alike, so on up to m books. So number of ways is equal to m times n whole factorial upon m factorial raised to n. Next we have a tricky question. Find the number of 5-digit words that 5-digit numbers that can be formed using the digits 0, 1, 1, 2, 3. I repeat, find the number of 5-digit numbers that can be formed using the digits 0, 1, 1, 2, 3. So number of 5-digit numbers is equal to I cannot start the first row with first element with 0. 1, 2, 3, 4, 5. I cannot fill the first blank with 0. So I can fill the first blank with 1, or I can fill the first blank with 2, or I can fill the first blank with 3. But here the given digits are 1, 1, 2, 3. So 1 is little bit different from 2 and 3. Little bit different from 2 and 3 because there are 2 copies of 1, and there are only 1 copy of 2 and 3. So number of 5-digit numbers is equal to 5-digit numbers that begin with 1 plus 5-digit numbers that begin with 2 plus 5-digit numbers that begin with 3. So how many 5-digit numbers I can form such that the first digit is 1? So you have to count how many 5-digit numbers are there which starts with 1. So how to count number of 5-digit numbers that starts with 1? So we have 5 blanks, 1, 2, 3, 4, 5. I can fill the first blank with 1 in one way. So after filling the first blank with 1, what are the objects that are left out? 0, 1, 2, 3. I can arrange these 4 objects in these 4 blanks in 4 factorial ways. Therefore, number of 5-digit numbers that start with 1 is going to be 4 factorial. Now, number of 5-digit numbers that start with 2. So once I fill the first blank with 2, once I fill the first blank with 2. So what are the objects that are left out? 1 0, there are 2 1s and 1 3. So I have to fill these 4 objects in these 4 blanks. So these 4 objects are not distinct. We have 2 1s. Therefore number of 4-digit numbers that start with 2 is going to be 4 factorial upon 2 factorial. Now number of 4-digit numbers that start with 3 is again going to be 4 factorial upon 2 factorial. So the total number of 5-digit numbers is going to be, total is equal to 4 factorial plus 4 factorial upon 2 factorial plus 4 factorial upon 2 factorial. So these are the total number of 5-digit numbers that can be formed using. Next we have a small problem. In how many ways the letters of the word cheese be arranged so that no two e's come together? So we have seen these kind of problems earlier. No two girls come together means what we do is we arrange boys first. After that we arrange the girls. So here no two e's come together. So what we have to do is we have to first arrange the remaining letters and then we have to arrange e's. So first let us write down the letters of the word cheese. So we have C H double E S E. So we have 3 e's which are identical, and we have 3 more letters which are different, C H S. So total we have 6 letters. Okay, so W1 is to arrange the remaining letters. That is C, H and S. So this can be done in 3 factorial ways. W2 is to arrange 3 e's in 4 gaps, because we have 4 gaps, 1, 2, 3 and 4. These are my 4 gaps. So I have to arrange these 3 e's in these 4 gaps. So number of ways of doing W2. So I have 4 gaps and 3 e's. So I can do it in 4p3 ways. But here these 3 e's are identical. Therefore we have to divide it by 3 factorial. So number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2. So which is equal to 3 factorial times 4p3 upon 3 factorial. Okay. Next, let us look into this question. Find the number of ways of arranging the letters of the word associations. In how many of these all the 3 s's come together, no 2 a's come together? So we have this letter association or associations. So in these associations we have 2 a's. So this is a little bit big word, so which contains 12 letters. Out of those 12 letters we have 2 a's and 3 s's and 2 o's and 1 c and 2 i's and 1 n and 1 t. 1 t and 1 n. So on the whole we have 12 letters. So the number of ways of arranging these 12 letters, number of arrangements is equal to 12 factorial upon, because all these letters are not distinct, we have 2 a's, so we'll divide it by 2 factorial, and we have 3 s, so we'll divide it by 3 factorial, and then we have 2 o's, we'll divide it by 2 factorial, and then we have 2 i's, so divided by 2 factorial. So these are the total number of ways of arranging the letters of the word associations. And the first one, so all the 3 s's come together. So all the 3 s's come together means you can tie up all the 3 s's. So once you tie up all the 3 s's, we have 2 A's and 1 unit consisting of S's and then remaining things. So on the whole we'll have 10 units. So tie up 3S. So now these can be, after tying up these 3 S's, so we can arrange these remaining letters, or we can arrange them in 10 factorial ways. But out of those 10 items, so there are 2 A's which are identical, so divided by 2 factorial, and there are 2 O's, so divided by 2 factorial, and there are 2 I's, so divided by 2 factorial. And then we can arrange 3 S's among themselves in 3 factorial ways. But those 3 S's are identical, so divided by 3 factorial. So these are the total number of ways of arranging the letters of the word associations in which 3 S's come together. And the second one is no 2 A's come together. So no 2 A's come together means first you have to arrange the remaining letters. So the remaining letters I can arrange in we have 3 S's. And after 3 S's we have 2 O's. And we have 1 C. And we have 2 I's. And then we have 1 T. And then we have 1 N. So I have arranged these 10 letters. After arranging these 10 letters, I will have 11 gaps. Namely 1, 2, 3 and so on up to 11. So I can arrange these 10 letters among themselves in 10 factorial upon. So W1 is to arrange these letters. This is my W1, and W2 is to arrange the remaining 2 A's in these 11 gaps. So W1 can be performed in 10 factorial upon 3 factorial times 2 factorial times 2 factorial. And W2 can be performed in 11p2 ways. But those 2 A's are identical, so we have to divide it by 2 factorial. So these are the total number of arrangements in which no 2 A's come together. First we have to arrange the remaining letters. The remaining letters can be arranged in 10 factorial upon 3 factorial times 2 factorial times 2 factorial. And then after arranging these 10 letters, we have 11 gaps. So I can arrange those 2 A's in these 11 gaps in 11p2 ways. But those 2 A's are identical, so divided by 2 factorial. Okay. Coming to the last problem. The last problem is regarding rank. Okay, so let me read the problem for you. If the letters of the word Ajanta are permuted in all possible ways, and the words thus obtained are arranged in dictionary order, then find the rank of the words Ajanta and Janata. So we have calculated rank we have seen rank problems earlier in 5A. But in 5A all the letters are distinct. Here all the letters are not distinct. So that is the only difference. So whenever you see these problems of this kind, first thing that you have to do is you have to arrange the letters in dictionary order. So first let me arrange the letters in dictionary order. So the dictionary order is going to be 1A, 2A's, triple A, J, K, L, M, N, this A, J and T. So this is my dictionary order. Now I have to calculate the rank of the word Ajanta. Rank of Ajanta. So this Ajanta starts with A. So I cannot count all the words that begin with A. So I can count all the words that begin with double A. So number of words that begin with, I cannot count all the words that begin with A, so I can count all the words that begin with double A. So all the words that begin with double A is going to be, I have to fill the first 2 blanks with 2 A's, and then we have 4 blanks. I can fill these 4 blanks using 1A, 1J, 1N and 1T. So these 4 blanks can be filled in these 4 letters can be filled in these 4 blanks in 4 factorial ways. So number of words that begin with double A is 4 factorial plus number of words that begin with triple A. But all the words that begin with triple A is same, come into this, is a subset of all the words that begin with double A. So I will not count all the words that begin with triple A. So the next thing that I will do is I will start all the words that begin with AJ. But unfortunately Ajanta starts with AJ. So I should not count all the words that begin with A and J. So I have to take one more letter. So I have to count all the words that begin with AJA. But Ajanta starts with AJA. So I have to take one more letter. So one more letter is going to be A. AJAA. So all the words that begin with AJAA is going to be NT. So I have to arrange this NT in 2 factorial ways. So 2 factorial plus all the words that begin with AJ, A, after A, the next alphabetical order is going to be N. AJAN. I cannot count all the words that begin with AJAN because my Ajanta starts with AJAN. So I have to take one more letter. So I also completed A, so I will take N, take A. All the words that begin with AJAN, A. So it's going to be 1 factorial. So I have already used 5 letters, so there is only 1 letter that is left out, so I can arrange it in 1 factorial ways. After that, all the words that begin with AJ, AN, after A, I can take T, A. So this is going to be 1. So this is my word 1, Ajanta. So rank is equal to 4 factorial plus 2 factorial plus 1 factorial plus 1. So if you want, you can count 4 factorial is 24 plus 2, 26 plus 1, 27 plus 1, 28. So rank of the word Ajanta is going to be 28. So here you have to be a little bit careful because the letters are repeated. So I can count all the words that begin with AA, but I will not count all the words that begin with AAA. Because all the words that begin with AAA is just a subset of all the words that begin with AA. So I should not count those things twice. So rank of Ajanta is going to be 4 factorial plus 2 factorial plus 1 factorial plus 1 factorial. I will count all the words that begin with AA. I will count all the words that begin with I cannot count all the words that begin with AJ. So I have to take one more letter, AJA. But Ajanta starts with AJA. So I cannot count all the words that begin with AJA also. I will count all the words that begin with AJAA, which is going to be 2 factorial. And after AJAA, I will count all the words that begin with AJANA. AJAN. But Ajanta starts with AJAN. So I have to take one more letter, which is going to be 1 factorial. And after that, we have the original word, so which is 1. Number of words that begin with AJANTA is 1. So rank is equal to sum of all these things. So if you understand this one, I encourage the students to pause the video and calculate the rank of Janata. Once you calculate the rank of Janata, you can check it here. So let me do the problem for you. Rank of Janata. So first what you have to do is you have to arrange all the letters in dictionary order. AAA, J, N, T. So I can count all the words that begin with number of words that begin with A. I can count all the words that begin with A because my Janata starts with J. So before J I can count all the words that begin with A. So number of words that begin with A. If I fill the first blank with A, then I will have 1, 2, 3, 4, 5. And I will have 2 A's, 1 J, 1 N and 1 T. I can arrange these 5 letters in these 5 blanks in 5 factorial upon 2 factorial ways because there are 2 A's which are identical. I have fixed this A, so I should not divide it by 3 factorial. Okay, all the words that begin with A plus all the words that begin with J. But unfortunately, Janata starts with J. So I cannot count all the words that begin with J. So after J, I have to take the next alphabetical order, it is A. So I cannot count all the words that begin with JA also because Janata starts with JA. So I can count all the words that begin with JAA. So all the words that begin with JAA is going to be 1, 2, 3. I have A, N, T. So I can arrange them in 3 factorial ways. After that I can count all the words that begin with JA. After A, the next alphabetical order is going to be N. But unfortunately Janata starts with JAN. So I cannot count all the words that begin with JAN. I have to take one more letter, that is JANA. But Janata starts with JANA also. So I have to take one more letter, that is A. All the words that begin with JANAA. So JANAA. I have used all the letters except T. So T can be arranged in that blank in 1 factorial base. Next, plus all the words that begin with JAN. After A, the next alphabetical order is T, because I have used J and I have used N. So the next letter is T. I cannot count all the words that begin with JANAT, because Janata starts with JANAT. I have to take one more letter, so which is going to be 1. This is my original word, so this is 1. Number of words that begin with JANATA is 1. Therefore rank is equal to sum of all these things, which is 5 factorial upon 2 factorial plus 3 factorial plus 1 factorial plus 1. So no need to expand, you can just leave it as it is. In permutations and combinations, we have completed permutations. Now we have to look into combinations. So as I have mentioned about permutations and combinations in the first lecture itself, so whenever order matters, if order matters, it is going to be a problem in permutations. If order does not matter, it is going to be a problem in combinations. So we can explain this using an example. Okay. Anyway, if order matters, we denote, we write those things in these brackets. If order does not matter, we write those things in these brackets. So these are set brackets, these are ordinary parentheses. Now, suppose you have a cricketing squad consisting of 15 people. You have a cricketing squad of 15 people. Now I have to select a team consisting of 11 people. Suppose you are there in this squad. So all that it matters to your parents is whether you are there in the team or not. So you are there in the cricketing squad of 15 people and your parents are waiting for the cricketing team. So the team consists of 11 people. So I have to pick 11 people out of those 15 people. All that it matters to your parents is whether you are there in the cricketing team or not. Now coming to this problem. So you have cricketing team of 11 people. Suppose you are there in this team. All that it matters to you is the batting order of batting. So whether you are the opener or the second one or the first down, second down, third down and so on. So here whether you are there in the cricketing team or not, that is going to be matter. So here order is matter, so it is a problem in permutation. So here it is a problem in combination. We'll announce those 11 names in these brackets. And we'll write those cricketing order in these brackets. Suppose if I write A, B, C, D and so on, so then what I will have is A is the first batsman, B is the second batsman, C is the third batsman and so on. So here if I write A, B, C and so on, then A is there in the cricketing team, B is there in the cricketing team, C is there in the cricketing team and so on. So here there is no notion of first element, second element and so on. But here there is a notion of first element, second element and so on. So in batting order there is a batting positions are there. But here in the cricketing team there is no position. All that it matters is whether you are there in the cricketing team or not. Okay. In general, number of combinations of n distinct objects taken R at a time is denoted by combinations are denoted by C of n comma r, or else we can use NCR, or else we can use this one. But in this chapter we will use this formula, this notation. And you should not read it as NCR. You have to read it as N choose R. So if you read it as NCR, you will not get anything. If you read it as N choose R, the meaning you can understand. You are choosing R elements out of N elements. Our next motto is to give the formula for NCR, or we have to count how many combinations we can have out of N dissimilar objects taken R at a time. And the statement of the theorem is like this. The number of combination of N dissimilar things taken R at a time is NPR upon R factorial. Number of combinations of N dissimilar things taken R at a time is going to be NPR upon R factorial. But number of combinations are denoted by NCR. Therefore, NCR is equal to NPR upon R factorial. And we know the formula for NPR. NPR is N factorial upon N minus R factorial divided by R factorial. So, NCR is equal to N factorial upon N minus R factorial times R factorial. So, this is the theorem that we have to prove. So, before looking into the proof of this theorem, let us look into this problem. The number of permutations of the letters of the word ABCD taken 3 at a time is 4p3. And I have listed down all the 4p3 elements. Let us look into the question. The number of permutations of the letters of the word ABCD taken 3 at a time is 4p3. And I have listed all the 4p3 elements. Now let me ask you this question. Number of combinations of four dissimilar things taken 3 at a time is 4 choose 3. Now we have to find out what is this 4 choose 3. I have these 4 objects A, B, C, D. I have to choose 3 elements. In how many ways I can choose these 3 elements? So since it is a small problem, I can list down all those 3 elements. So the 3 elements that we have is ABC, ABD, and then ACD, and then BCD. So these are the combinations that we have. We have 4 distinct elements. I have to take 3 elements at a time. So if I take 3 elements at a time, then these are the 4 combinations that I will have. These are the distinct combinations that I will have. And these are the distinct permutations I will have. If you observe, this combination ABC results in these 3 factorial permutations. This combination ABC results in these 3 factorial permutations. Similarly, this combination ABD results in these 3 factorial combinations. Similarly, the next one ACD results in the next 3 factorial combinations. Similarly, the next one BCD results in these 3 factorial combinations. That means every set containing 3 elements results in 3 factorial combinations. Similarly, every set containing 4 elements results in 4 factorial combinations. So if you observe this, if you understand this one, then we can give the proof of NCR easily. So here the number of combinations is going to be 4p3. So 4p3 upon 3 factorial. So which is equal to 24 upon 6, which is equal to 4. So these are the 4 combinations that we can have. Anyway, we will try to establish this one using the theorem. So using the theorem, we can do it for large N and large R. Okay. So number of combinations of n dissimilar things taken r at a time is npr upon r factorial, that is ncr is equal to npr upon r factorial, but npr stands for n factorial upon n minus r factorial, therefore ncr turns out to be n factorial upon n minus r factorial times r factorial. So let us try to give the proof of this one. Let the number of combinations of n dissimilar things taken r at a time be NCR. We have to find out what is this NCR. So as we have seen in this example, one set containing ABC will result in 3 factorial permutations. Therefore, one combination results in R factorial permutations. In fact, R factorial different permutations. This implies NCR combinations gives NCR or n choose R times R factorial permutations. N choose R permutations, n choose R combinations gives rise to n choose R times R factorial permutations. But total number of permutations is equal to total permutations of n objects taken R at a time is NPR. So this implies n choose R times R factorial is equal to NPR, or n choose R is equal to NPR upon R factorial, which is going to be n factorial upon n minus R factorial upon R factorial, which is nothing but n factorial upon n minus R factorial times R factorial. So we have given the proof of this one. N choose R is equal to n factorial upon n minus R factorial times R factorial. So for this we have taken the example, help of this example. Next, NCR is equal to NPR upon R factorial, but NPR is equal to n times n minus R, n minus 1 times n minus 2 times so on up to n minus R plus 1, and R factorial is equal to R times R minus 1 times R minus 2 so on up to 2 times 1. Therefore n choose R, I can write it as product of n consecutive, product of R consecutive terms in the numerator by product of R consecutive terms in the denominator. So the numerator is product of R consecutive terms, and denominator is also product of R consecutive terms. But the numerator starts, in the numerator and these R consecutive terms, product of R consecutive terms, these R consecutive terms starts with n. In the denominator, the R consecutive term starts with R. Numerator starts with n and the denominator starts with R, and we have to go up to R places. If you go up to R places, the denominator will hit 1 and the numerator will hit n minus R plus 1. Okay, so let us look at some examples. So if you look at 10 choose 4. So 10 choose 4 means I have to start with 10, I have to go 4 places. 10 times 9 times 8 times 7 upon 4 times 3 times 2 times 1. So if you write down 11 choose 2, which is equal to 11 times 10 upon 2 times 1. So this expansion will help you in solving a few problems in exercise. So you should not neglect this expansion. Next, number of combinations of n dissimilar things taken R at a time is n choose R. We can generalize it like this: number of subsets of R elements out of a set containing n elements is going to be NCR or n choose R. I repeat, number of subsets of R elements of a set containing n elements is n choose R. The number of subsets is going to be n choose R. The number of number of subsets containing 2 is going to be n choose 2. Number of subsets containing 3 elements is going to be n choose 3. Number of subsets containing R elements is going to be n choose R. Okay. Now we have an interesting theorem. If 0 less than or equal to R less than or equal to n, then n choose R is same as n choose n minus R. So n choose R is same as n choose n minus R. Suppose you have a class containing 70 people. I have to select 60 people. Suppose you have a class containing 70 people. I have to select 60 people. The number of ways of selecting 60 people out of 70 people is 70 choose 60. So instead of selecting 60 people, what I do is I am a little bit lazy so what we do is instead of selecting 60 people, I remove 10 people from the class. If I remove 10 people from the class, still I am going to get my 60 desired people. Therefore, number of ways of selecting 60 people is same as removing 10 people. So in order to remove 10 people, I have to select 10 people. So 70 choose 60 is same as 70 choose 10. So here n is my 70, R is my 60. 70 choose 60 is equal to 70 choose 70 minus 60, which is nothing but 10. So number of ways of selecting R elements is same as number of ways of removing n minus R elements. So the first proof is like this. Number of ways of selecting R elements. Number of ways of selecting R elements is same as number of ways of removing n minus R elements. So in order to remove n minus R elements, we have to select n minus R elements. Therefore n choose R is equal to n choose n minus R. So that is one way of proving the theorem, and the second way of proving the theorem is using the formula. So n choose n minus R is equal to n factorial upon n minus of n minus R factorial times n minus R factorial. So which is equal to n factorial upon R factorial times n minus R factorial. This I can write it as n factorial upon n minus R factorial times R factorial. So this is nothing but my NCR or n choose R. I have started with n choose n minus R and I have ended with n choose R. Therefore n choose R is same as n choose n minus R. So you should not remember the proof like this, you have to remember the proof in this way. Number of ways of selecting 60 people is same as number of ways of removing 10 people, or number of ways of selecting R people is same as number of ways of removing n minus R people. In order to remove n minus R people, what we have to do is we have to first select n minus R people. I repeat, n choose R is equal to n choose n minus R. This is an important theorem, so you have to remember. N choose R is equal to n choose n minus R. N choose R stands for number of ways of selecting R people or R objects from n objects. N choose n minus R stands for number of ways of selecting n minus R objects from n objects. These two are same. Selecting R objects is same as removing n minus R objects. Okay. So with this I will end the lecture.